Hello, good morning. I hope you are all doing great. Today, inshallah, I will continue the last lecture about the use of matrices in vector spaces. We already covered four main applications of using matrices in vector spaces. In this additional, and this is the final one, application in chapter 5, also from the plenty of ideas that you can use in order to make your life easier in checking the various applications in vector spaces is to check if two sequences of vector generate the same vector space or not. In order to judge this issue, the process is really very simple. I will keep it as simple as possible. All I have to do, if I have U sequence and the V sequence, so I have two sequences, and if I want to know if these two sequences of vectors of N are the same or they can cover the same vector space, this is very, very simple. All I have to do is to use my matrix with either the vectors as rows or as columns. The main application, according to our slide, as we saw previously, I can do both. So if we want to describe it on rows, the process is really very simple. All I have to do is to use the vectors as rows in the matrix of the basis, and then I will start doing row operations. If you remember the row operations or the lines operations according to the slides, which is multiplying row by a number, switching rows, or multiplying a row by a number and adding it to another row in order to get a reduced echelon form. So I will take the first sequence and do the row operations to reach the reduced echelon form. And for the other sequence, I will do exactly the same, trying to reach the reduced echelon form. If the two reduced echelon forms are the same, then the two bases for this vector space are also equal, and they can generate this vector space. The idea is really very simple, as you can see. So if we want to check this idea on a problem, it's not going to be difficult. It's really very direct application for the use of matrices. So let's check this sequences. Here you are given three sets of sequences. The first set consists of the first vector, second and third, which contains three vectors. The second set contains two vectors, and the third one contains also two vectors. I want to check if they can generate the same subspace of R3. The idea is really very simple. All I have to do is to take these vectors, putting them on the matrix, and trying on the matrix of the basis, and trying to reach a reduced echelon form. Either by row or either if you consider the vectors as rows or you consider the vectors as columns, it will make no difference. I will do it as rows according to our slides. So let's start by getting the reduced echelon form for each set of these sets. So for the first set, I will take the first vector to be the first row, the second vector to be the second row, and so on for the third one. Fixing the first row and multiplying the first row by -2 and added on the third row, I will reach this form. Of course, it's really very obvious. If you multiply the second row by -1 and adding it on the last row will be zeros. Now I have an echelon form, as you can see, so all I have to do is to add the second row once more to the first row according to the description. Now you have your reduced echelon form. Let's check also if I did the same sequence or if I did the row operations with the other basis, am I going to reach this result or not? So I will start with the second sequence, which is 1, 0, 4, 3, -2, and 4. And also, I will start working our magic by the row operation order to get a reduced echelon form, which is very, very simple. I will multiply the first row by 3, negative 3, I'm sorry. Then I will add it to the second row. So the negative 3 plus 3, the result is 0. Negative 3 times 0, which is 0 plus negative 2, it's going to be negative 2. Negative 3 times 4, it's going to be negative 12, plus 4, it's going to be coming to negative 8. Now, if I divided the second row on negative 2, we will end up having 0, 1, and 4, which is actually the same reduced echelon form, the same number of non-singular rows with the same numbers. This means that the first two sequences are exactly the same, and they can represent or generate the same subvector space. Let's now check for the third one. Is it gonna be the same or different? So in a similar manner, with the same steps, I will take these two rows, put them in a matrix, and trying to reach my reduced echelon form. The steps are really very simple, but if you remark, the reduced echelon form in this case is different than the other two sequences, which means that for the first and second, they both generate the same vector space. But for the third one, it's not generating the same vector space. So that's our conclusion. See, the steps is really very simple. All I want you to do is to just remember these steps while you are working. It's really very simple, but you have to do it with your hand. Now you can remark that dealing or using matrices, it is exactly tools in your hand to use them the way you like it, either for independence, either for checking if a vector belongs to a certain basis or a certain subvector space, or like this problem, how to check if you have two sequences, if they can generate the same vector space or not, or the same subvector space or not. We just saw that the problems previously stated in the beginning of this section, the 5 applications, are all dedicated for the dimension with Kn. It means that we did deal with R2, R3, R4, or whatever. Okay, the question is, what's going to happen if we are dealing with polynomials and if we are dealing with matrices, for example? Or, I'm sorry, for example, or what I want to say, already we defined previously a vector space as a collection of vectors or objects all together working or under the addition closure, the multiplication by scalar closure, and you have all these conditions. So it can be applied for vectors, for polynomials, for matrices, for functions, or for operations in general. The key is exactly like what we did, using this issue with R2, R3, R4, or K2, K3, K4, either for real numbers or for complex. Is it gonna be different if we do the same with another type of applications? Let's discover this. The answer is really very simple. They are exactly the same sequences, but the parts that you use in your basis, it will be different depending on the vector space nature that you are dealing with. So for any vector space E of dimension n, by choosing a basis beta of E, like f such that E belongs to K of n, you will contain beta 1 up to beta n, which are vectors representing this the generation of this subvector space or vector space. And of course, using the coordinates, you can, by the linear combination, construct any vector. So once more, f such that E into Kn, and U is the set of vectors that's the basis of this vector space or subvector space, whatever, that maps each vector U into E to a sequence of coordinates, which is the coordinates relative to the basis in order to generate this vector. So simply it's going to be E1, beta 1, which is a constant, times E1, and so on. We usually refer to E1, E2, E3 in all of them as the standard or the canonical, which is the simplest basis for this subvector space. Of course, it is a bijection, which means it is injective and surjective. That's the meaning of bijection. Solving problems that use vectors of E, other objects like polynomials or like matrices, all you have to remember is the dimension which is related to the nature of the objects. The dimensions for Kn, like Rn, R2, R3, R4, it's equal to the n. But in case of polynomials, the dimension will be R plus 1. So exactly can be done, 10 steps for discovering these facts, respectively, with vectors of k to the power of r plus n plus 1, or polynomials. And we will take an example. And for matrices, the dimension will be, as we stated previously, it will be m times n. By using their sequence of coordinates with regard to the chosen basis, we can generate either matrices or polynomials. We already tried, if you remember, if I have a matrix 2 by 2, for example, I will have 4 basic vectors. I can call them vectors or pre-matrices or standard form matrices, which are 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and 0, 0, 0, 0, 1. And those E1, E2, E3, E4 can generate any 2 by 2 matrix, belongs to the set of either real or complex numbers, just by multiplying by a set of coordinates alpha 1, alpha 2, alpha 3, alpha 4, belongs to K, either real or complex. The same previous argument can be used in any vector space E of finite dimension, and therefore still using matrices to solve these problems exactly. I believe we need an example to show you how it's gonna be. Let's think in R3 of X, which means a polynomial or the third degree polynomials. And in specific for this subvector space, where you have the first is x cubed 4x squared 3x plus 6, the second vector is 2, and the third vector is 2x cubed 8x squared plus x plus 3. The idea here, how to twist your knowledge in order to absorb such a thing, which is really very interesting. Let us think first. If you have if you have a polynomial of third degree, it means that the basis will be with 4 coordinates or with 4 main vectors in order to generate the x cube the x cube equations. So I will go for taking the vectors that's gonna form the R4 or the R3 of X as x cubed, then x squared, then x, then 1. And I will consider the coordinates, which are 1, 4, 3, and 6. So it's already the first vector can be generated from E1, E2, E3, E4, where E1 is x to the power of 3, E2 is x to the power of 2, E3 is x, E4 is 1. Now, taking or considering the basis to be x cubed, x squared, x plus 1, according to the linear combination, I can multiply, all the these vectors by the coordinates. In my case, for the first vector, the coordinates will be 1, 4, 3, and 6. And the same for the second, third, the same for the second and for the third. Simply, the vector coordinates for the basis, the first basis, are 1, 4, 3, and 6. For the second set, it's gonna be 0, 0, 0, and 2. For the third set, it's gonna be 2, 8, 1, and 3. So simply, we can use beta, the sequence of coordinates of the first one is gonna be 1, 4, 3, and 6. The second one is gonna be 0, 0, 0, and 2. The third one, which is gonna be 2, 8, 1, and 3. I can consider x cubed, x squared, x plus 1 as the canonical or the standard basis for the K4. Now I have the coordinates that's gonna form this subvector space, which is simply the sequence like this: 1, 4, 3, 6, 0, 0, 2, 2, 8, 1, 3. According to this set, I can now check the independence, of course, and of course, I want you to remember, in order to generate a subvector space of x3, I will need another vector in order to have four vectors. That's gonna be, and this is how we are going to be able to generate this subvector space. Let's check if we are using the same vector coordinates, and I would add 0, 1, 0, just in case, in order to check if this is gonna cover R4 or not. It's really very simple. So all I have to do is exactly like what we did previously, which is simply putting these vectors in a matrix, as you can see, and I can check their independence or not with the same sequence that we did previously. Vectors of R3, which is in the basis x cube x squared x1, has the coordinate sequence 0, 1, 0. That's the new vector, which means x squared. Okay, hence these are linearly independent sets, and this is very easy to check if you try to construct your matrix using either rows or columns 1, 4, 3, 6, 0, 0, 2, 2, 8, 1, 3, 0, 1, 0, 0, and you will have a rank of 4, which means they are linearly independent. That's a very nice problem to show you how to deal with polynomials. And it's exactly the same in the case of matrices, and we will see it down the road. Now, for this example, which is a standard example, plenty of times you will have a problems like this embedded in the exams, as we will see later, inshallah. Here is giving you an example. Let E be a vector space such that beta consists of E1, E2, E3, E4, and they are the basis of E. Let's check the sequence. The first vector of the sequence that generates E that we want to check is E1, E2 plus E4, which means you will add 1, 0, plus 0, 1, 0, plus triple zeros and 1 to each other. And this is going to form the first vector. And for the second vector, I want to check if 2e1, 2e2, e3, and e4. That's another way of giving you a vector. So write the standard basis, e1, e2, e3, e4. The sequence of bases that I want to check contains v1, which is 1, 1, 0, 1, as we saw from adding these standard bases, standard vectors in the standard basis, which is, as I told you, 1, 0, 0, 0, 1, 0, 0, 0, and 1 all together, and you will have this vector. In a similar manner, also, I will multiply 2 in 1, 0, 0s, 2 times 0, 1, 0, and then 0, 0, 1, and 0, and then 0, 0, and 1, and you will have your second vector. Let's check if they are independent or not. And this is really very simple. All I have to do is to put them either in rows or columns. I usually, as you saw previously, I prefer to use columns. So I've taken the first row, the first vector as a first column, and the second vector as the second column. Then I will work with the row operation, multiplying the first row -2 and -1, I'm sorry, and add it on the second row, then multiplying the first row -1 and add it on the fourth row, and that's how it's gonna be the matrix. Going to a reduced echelon form in order to check the independence between of them. And here we go, that's the echelon form. The rank is equal to 2, which means these two vectors are linearly independent. Since they are linearly independent, I can check and continue adding vectors in order to get a basis. So extending this set of vectors, this vector, the first and the v1 and v2, in order to be able to generate the R4, it's very, very simple. I will choose two of them. There is no restriction on how to choose, but I've chosen one triple zeros, 001 and 0, and I want to check if I added E1 and E3, is it gonna work or not? So once more, I will use row reduction, and I've ended up having a 4 by 4, I'm sorry, a rank of 4 for the matrix of the basis of vectors, which means those 4 vectors are linearly independent, so they can't be generated from each other. And so we can S at this form, which is V1, V2, and E1 and E3 can generate R4. In a similar manner, if I want to use uh, 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 2 with vectors as rows, it's exactly the same. It's linearly independent, extending the sequence to E. I can use other vectors if you like. These are my 2 vectors. I'm going to put them in a matrix to check the independence. Yes, it's with rank 2, so they are linearly independent. I can add 2 another vectors. We choose other vectors like 0, 1, 0, 0, and I've added 1, 1, 0, and 1 to my set. So extending the basis of R4 by adding 2 vectors, E2 and E4. Let's try them. This is E2 and E4. And here we go as rows. This is E2 and that's A4. And also, if you try to reach a reduced echelon form or an echelon form, you will end up having a rank of 4, which means they are linearly independent. And so the set that can generate R4 is V1, V2. Now you have E2 and E4. So in this example, we saw that we can generate more than one basis to generate the same vector space as you saw. Using E1 and E2, these are as you saw, E2 and E4, and in the previous action we already used E1 and E3. So it's linearly independent and dimensions equal to 4 and can generate E. By the end of this application, we already now finished chapter 4 officially, and I will start with the next week, inshallah, to work with linear transformations, which is chapter number 5, inshallah. Please try to study all of these chapter 4 very well. And remember, for the second midterm, it will start covering from chapter 4, 5, 6, 7, and 8. So the time is kicking and we need to work as fast as possible. Thank you very much for watching this video, and I wish you the best in your academic endeavors. It's my pleasure to be with you, and I will see you next week, inshallah. Thank you very much. Thank you. Bye bye.